Yeah, so the recording has been started. So there is some problem with question number D, like the solution. F minus g whole square is a constant. That doesn't mean that f minus g will be a constant. So I have claimed here this directly because if you have some function f minus g is suppose minus some z naught and z naught under some condition, and then that will imply what? F minus g whole square is a constant, and namely this constant is actually z naught square. But you see, f minus g whole square is a constant may not imply that f minus g is also a constant. But in this case, why is this true? Like f minus, from here, why can I conclude that f minus g is a constant? Because C is connected. So this is a very important justification that you have to mention. To conclude that f minus g is constant, from f minus g whole square is a constant, you have to justify that C is connected. Because C is connected, so this will happen because it cannot take two different values. Okay, and just always okay. 5a also I had also shown here, and 5b, what was the question? You have to find the power series of this function, and you have to prove that this function, if the power series is suppose a0 plus a1z plus dot dot dot, then you have to prove that a2n plus 1 is 0 for all n in natural number, and a0, or basically what you have to prove that a1 is minus half, no, or you have to find a1. So again, there are many ways to solve this question. Okay, so one way, you see, you have to prove that all the odd terms are 0, right? Odd coefficients are 0 except a1. So for that, you write, or basically any function f can be uniquely written as a sum of even and odd function. So this fact is very much clear. Why? Because fz can be written like this: fz plus f of minus z by 2 plus fz minus f of minus z by 2. So this is the even part, this is the even part, and this is the odd part. Okay, so let's talk about the odd part. So the odd part is f of z minus f of minus z by 2, so which is z by e to the power z minus 1 minus e to the power minus z by, sorry, this is minus z by e to the power minus z minus 1 whole divided by 2, that is multiplying by half. You have to simplify this a bit. So if you simplify this, so this will come how much? So z by e to the power z minus 1 plus z, this will become e to the power z minus 1 sorry. So this is, if you just simplify this, 1 by e to the power z minus 1, if you take LCM, so this will become e to the power z will come here, and this will become 1 minus this. So if I write here minus, this is simple calculation that you can do. If you now take the LCM, so this will become z minus z e to the power z by e to the power z minus 1 half times, if I take z common, then things will get cancelled and there will be minus. So you can see that what I am getting, this has power series, if I expand the odd part in terms of power series, it will have a1, a3, a5, that you know that for an odd function only the even ones will get killed and only the odd one will remain, and here this will have the coefficients a2, a4, a6 and so on, and even a0. So all the odd coefficients of the power series of fz will come from this odd part only, and what I am seeing, that odd part is minus half z, so therefore a1 is minus half, and all other coefficients of z cube, z to the power 5 are all 0. So a 2n plus 1 is 0 for all n in natural number. So this was some sort of justification. There are many other methods, but this was the simplest of all. Okay, so this was the solutions to minor. So now sir has done so many things like maximum modulus principle, Mobius transformation. So I'll pick some questions from these topics. So the first question that I want to take from maximum modulus principle, this is from number 10 of Joseph Back. Find the maximum and minimum modulus of z square minus z in the disk This is the question. Let's solve it. So if I call this function as fz, which can also be written as z into z minus 1. So how to start? Any approach, any idea from your side? Any approach from your side? Like how to find the, like you have to find the maximum of this and the minimum of this. Okay. You cannot talk about the maximum and minimum of just fz because the field of complex number is not ordered, so you cannot talk about this. So what is your approach?
As fz is analytic and non-constant, then maximum attend only on boundary. So we check at mod z equal to 1.
Right. So first you see, let's apply all the conditions to for maximum modulus principles to be true. So because if z is analytic on the interior of this one on this. So the maximum, because this is a polynomial and polynomials are entire, by the way, so the maximum of modulus fz will be attained on mod z equals to 1. So what does the maximum modulus principle says? It says that the maximum value of modulus of fz will be attained on the boundary. So here the domain is the unit disk along with this boundary is this and the interior. So by the maximum modulus principle, the maximum can achieve only on this unit circle, not in the interior. Right. So how to find the maximum then? So let mod z equals to 1. So let's determine modulus of fz. So which is modulus of z into z minus 1. If I apply the properties of modulus, this is mod z and mod z minus 1. Right? Mod z is 1. You can see mod z by my condition is 1. So mod z is 1. I'll simply eliminate mod of z minus 1. If I use the triangle inequality, this is mod z and modulus of 1, which is nothing but 2. So therefore, modulus of fz is indeed less or equals to 2 on or for all z such that mod z is 1. So can I say the maximum is 2? So the maximum will indeed be 2. I can show that because modulus of fz is less or equals to 2. If I can find one point on the boundary of the circle, on the unit circle at which fz is 2, then we are done. So clearly we check it minus 1. So f of minus 1 is what? Minus 1 into minus 1 minus 1, which is 2, I guess, right? So therefore modulus of f of minus 1 is 2. What is the maximum? So therefore maximum of modulus fz on this is nothing but 2. So this function can take the maximum value 2 in the interior of the closed unit disk. So is the explanation clear or not clear?
Yes, sir.
So what about the minimum? What about the minimum?
0, sir.
Right. You can clearly see this function takes the value 0 at z equals to 0. So we are done because modulus of some complex number cannot be less than 0. So and clearly as f of 0 is 0, so minimum of the function, minimum of the modulus of the function at this is nothing but 0. So there are different ways to do this question. So I'll pick up another question. This is from another book. So another question. I'll just talk about the maximum of this function. Find the maximum of this function on mod z less or equal to 3. So this is 3z minus 2i. So again, if you follow one process this way, then also you can proceed. Let me proceed with this. So one way is this. So again, fz is analytic on mod z less than 3. So by the maximum modulus principle, the maximum of mod fz is attained on the boundary, right? So attained on mod z equals to 3. So if we start in the similar manner, so 3z minus 2i, if you apply the triangle inequality, so this is 3 times modulus z, right? And then plus modulus of 2i by the triangle inequality, and mod z is 3, so this is nothing but 3 3 is a 9 plus modulus of 2i is 2, and this is 11. So you can conclude that maximum of this at mod z lesser equals to 3 is nothing but 11. There is one way, another way of doing this. So the first part is clear that fz is analytic on this, so the first part will be there, but let mod z equals to 3, then z is of the form 3 e to the power I theta, right? So now use this. So at sometimes this you can also proceed in this manner. So 3z minus 2i, which is nothing but 3 times 3 e to the power I theta minus 2i. This is nothing but 9 e to the power I theta minus 2i. So you have to find the modulus of this complex number. So it is very easy. So e to the power I theta is cos theta plus I sin theta. So this is cos theta plus 9i sin theta minus 2i. What is the modulus of this complex number? Root over of the real part is this and imaginary part is this, right? Right. So this is 9. Yeah. So this is 9 cos theta whole square, and what is the imaginary part? 9 sin theta minus 2 whole square. So what is this? So this will become root over of, just simplify. So this is 81 cos square theta plus 81 sin square theta plus 4 minus 2ab, right? So that will become 36. So the first two term will become 1, right? Because cos square theta plus sin square theta is 1. If I take 81 common, so 81 plus 4 is 85. So 85 minus, if you see this, modulus of fz is same as square root of 85 minus 36 theta, and you have to maximize this term, the last quantity, you have to maximize this quantity for theta. So when is this maximum? So this is maximum when sin theta is minimum, right? Because there is a minus in between. So when will this square root be? Square root can take more and more value when this sin theta is minimum. So when is sin theta minimum? That is sin theta equals to minus 1, and sin theta equals to minus 1 at theta equals to minus pi by 2. Or this is not required. So only sin theta is minus 1. When is sin theta minimum? When at theta equals to minus pi by 2, and at that minus pi by 2 sin theta is minus 1. So what is modulus of fz, or maximum part. So maximum at mod z less or equals to 3. This is root over of 85 plus 36 because sin theta is minus 1 and that is root over of 121 which is 11. So if you are also applying this method or you are applying this method, in both the ways you will get the same answer. So if you want to ask anything, you can ask. Okay, so let me talk about Mobius transformations a bit and then we'll solve something on Mobius transformation as well. So then let me talk about so dz is of the form az plus b by cz plus d where AD determinant is not 0 minus BC is not 0 and ABCD are complex numbers. A, B, C, D are all from the set of complex numbers. So my first question is if T is so let me collect all the Mobius transformation in a set. Okay, so let me collect. So let this script M with a collection of all the transformations such that T is a Mobius transformation. Okay, so my set M is the collection of all Mobius transformation. So what is the result? This set along with the composition of function forms a group. So this is very interesting fact. The collection of all the Mobius transformation under the composition of functions or compositions of maps forms a group. So tell me the properties of a group very quickly. What is the first property of a group? Sorry?
Closed-ended addition.
Sorry. Could you please repeat again?
Closed-ended addition.
Not addition here. What is the composition? What is the binary operation here?
Composition. Closed-ended composition.
Right. So the first thing that I have to prove is that this set M is closed under composition. So this is a very calculative job, but anyways I'll do it and you can also try by yourself. It's easy but bit calculative. So for which, so the first property number 1, closed under this, right? So for which let T Z be AZ plus B by CZ plus D and SZ be A prime Z plus B prime by C prime Z plus D prime belong to M. So I have taken two Mobius transformation. That is what I know, that AD minus BC is not 0 and A prime D prime minus B prime C prime is not 0. I will first find out the composition, that is T composition S at Z, or you can also find S composition T. So T of Sz. So what is T of Sz? So this is A plus B divided by C plus D. Instead of Z, Sz will come, and what is Sz? A prime Z plus B prime by C prime Z plus D prime, and then A prime Z plus B prime, and then C prime Z plus D prime. So please simplify along with me and tell me if I make some mistake. So this is A prime Z plus A B prime plus B C prime Z plus B D prime, and this is C A prime Z plus C B prime plus C prime D Z plus D D prime, and those things will get cancelled. So this is also Mobius transform. So this is also of the form this something Z plus AB prime plus BD prime C A prime plus C prime D at Z plus CB prime plus DD prime, right? So when will decomposition S belong to M? This belongs to M if the determinant, which is A prime plus BC prime times CB prime plus DD prime minus C AB prime plus BD prime times CA prime plus C prime D, this is not 0. Am I correct? When will decomposition S belong to M? That is, when will decomposition S will be a Mobius transformation? When the determinant, which is this into this minus this into this, will not be 0. If I can show this condition, then we are done. If I can show this condition, then we are done. So let me start by evaluating this. So which is A prime plus BC prime. This is just a calculative job. It's easy. You have to just calculate a bit. So let's simplify this quantity. If you simplify this, okay, I'll just write it down. A prime C B prime, just multiply A prime D prime plus BC prime CB prime plus BC prime DD prime minus AB prime CA prime minus AB prime C prime D minus BD prime CA prime, and then minus AB prime C prime D. Sorry. Last term is BD prime C prime D. So few things will get cancelled for sure. This will cancel with A prime will cancel with which one? Can you tell me? This term, right? You can see. Please check. And this term will cancel with BC prime. I guess with the last term, right? It has B, then C prime, D, and yeah. So this will get cancelled. So what I am remaining with? So from this and from this, you take AD common. If I take AD common from the first and from this term and this term, I'll remain with A prime D prime minus A prime C prime. No, I'm taking AD common, so B prime C prime. Am I right?
Yes, sir. Yes, sir.
And from these two terms, if I take BC as common, I'll get B prime C prime minus A prime D prime. So so you see from here, if I take minus also common, so this will become A prime D prime minus B prime C prime. So if I take A prime D prime minus B prime C prime as common, I'll remain with AD minus BC. And this is non-zero. Do you agree why? As A prime D prime minus B prime C prime is non-zero and AD minus BC is also non-zero. So these two are non-zero, that will definitely guarantee that this is also non-zero. So do you agree? So therefore T composition S is in M whenever T and S are in M. Okay. So the first condition has been satisfied. What is the second condition of a group to form a group?
Associative.
Right. So that comes from the fact that composition of functions. So as composition of functions is associative, you know this fact. So M or so this is associative under. So we are done with the second property also. Third property, existence of identity. So let IZ be the identity transformation. Then I is a member of M because its determinant is non-zero, and for any T in M, I composition T is same as T composition I is same as T, right? So you can very much easily check. So this is the existence of identity. And number 4, the existence of inverse. So define the inverse transformation. Let Tz be Az plus B by Cz plus D, where AD minus BC is non-zero, or that is pick any member from M. You have to find the existence. So define, this is just a symbol, T inverse Z like this. So it is dz minus B by minus Cz plus A. Then look at the determinant. Determinant is again AD minus BC. So this minus this is again non-zero. So then I need to write this. Then T inverse also belongs to M, and if you compose T with T inverse or T inverse with T, you will definitely get identity. Therefore, this is a group. So sometimes we will simply write M is a group without writing the binary operation that it is composition of function. So when I'm writing that M is a group, so you understand that it is a group under the composition of functions. So this was a very easy thing. Any problem? Okay. So the reason why I did this is because of a question. So now let me pick up a question from Conway. So this is exercise 26 of Conway. What they are saying, let GL to C. What is this? This is the general linear group of order 2 under C. Okay. So what is this? This is all invertible 2 by 2 matrices with entries in C. So there are two parts to this question. This is the first part in C. So is this a group?
Yes, sir.
Is there to see a group? Yes. Group under what is the binary operation here?
So multiplication of matrices.
Right. So I should actually write, they have not written the question, but this is indeed a group. So group of all invertible 2 cross 2 matrices with entries in C. This is indeed a group, and let M be the group of Mobius transformation. So now you know that this will be a group. M will be a group. I have proved that Mobius transformations. So I have a group of 2 by 2 matrices, invertible matrices, which is a group under multiplication, and I have group of all Mobius transformation, which is a group under the composition of functions. So do not get confused. I have not written the binary operations, okay, but you remember this is a group properly. So GL2C comma, this is matrix multiplication. So this is a group, you know. So this is a group, and M comma composition of functions. So let me write composition of functions. So do not get confused with both the things. Here the operation is there, so R groups. So this is given in the question. Now let's read the question a bit further. So define, we are defining a map phi like this, okay? We are defining phi from GL to C to M. So we'll pick up a we'll pick up an invertible matrix, and so we'll pick up an invertible matrix. So phi at A, B, C, D. We are sending this to a Mobius transformation AZ plus B by CZ plus D. Right? So is this map defined? Is it correct, the definition?
Yes, sir.
Yes,
Right.
sir.
Yeah. So why is this a Mobius transformation?
Because
Because CD minus BC is non-zero, is guaranteed by the fact that ABCD belongs to GL2C. Okay, so that means the determinant will not be zero. But instead of GL2C, if I take the collection of all all matrices, then this map may not be well defined, because then the right hand side will not be a Mobius transformation. Okay, but one more thing is interesting. Show that phi is a homomorphism. So this is not just any map. This has one extra property, that this map phi is a group homomorphism. So I'm linking group theory with complex analysis. So that phi is a group homomorphism. So what is a group homomorphism? So can you tell me? So I have a map F, and G1 is a group and G2 is a group. So when will I call F as a group homomorphism?
If fx1 star x2 equal to fx1 with any triangle with fx2 means two binary composition, one is star 1 and one is star 2
Right.
respectively g1 and g2.
Right, that's correct. So if the composition here, so here if suppose it is suppose it is star and suppose it is triangle, then this should be equal to fx triangle fy. So what you said is correct. So just keep the definition in mind. We'll use this. So show that this is a group homomorphism, and not only that, this is a group homomorphism of GL2C onto, you have to also prove that this is a onto map onto M, and you have to also find the kernel of. So let's start the solution. So I have to first pick two matrices. So let A, which is A, B, C, D, and B as A prime, B prime, C prime, D prime, this both be from this. So what is known to us that AD minus BC is not 0, and A prime D prime minus B prime C prime is not 0 is given to us. And not that is, we have basically, we have this to show. Now who can tell me what I have to show? To show, how to show that phi is a group homomorphism? Tell me how to show that phi is a group homomorphism.
Multiplication of a and b.
Sorry, could you please repeat again?
First multiply a and b,
Right,
then calculate phi of ab in terms of that transformation.
right. And this should
Then
be same as
phi
Phi
a
of A.
composition phi b
phi of A
composition.
composite phi of B, because now phi of A is a Mobius transformation and phi of B is a Mobius transformation. So see here, this is the matrix multiplication. So here I have used the matrix multiplication and here I have used the composition, right? So that is the easy job. I hope you can do it. You just, so this I leave up to you. So just you have to calculate and everything. I have already calculated the composition here. You can check that, right? I have calculated the composition here. So I'll just, okay, let me try to do it. Should I do it or will you try? Tell me.
Yes, sir, you can left.
Okay, I have to do it.
No, sir.
Okay, you all can try this fact. So remember, on the left hand side, what is the thing? On the right hand side, what is the thing? If you are unable to do it, you tell me, I'll do it. So this is your exercise to do. So what else? This is a onto homomorphism. So this is a onto homomorphism. So how to prove that it is onto? So now for the onto part, just use the definition. Let you pick up any Mobius transformation M from M. So let Tz equals to Az plus B by Cz plus D, and AD minus BC is non-zero, belongs to, so this condition has been given to us, belongs to M. Okay, or basically I should not write this here because if I am picking a member, that is enough, right? So how to prove that this is onto? You pick up a member from the right hand side. So on the right hand side we have a Mobius transformation. So I have picked up a Mobius transformation T from M. Then what I know is that if this is, so then if this is a Mobius transformation, then AD minus BC is non-zero. If I define a matrix, like this, A, B, C, D, then determinant of A, which is AD minus BC, by this above condition is non-zero. Hence, A belongs to GL2C, and what is the image of A, which is AZ plus B by CZ plus D, which is nothing but D. So therefore phi is onto. Is the proof clear or not clear?
Yes, sir.
Okay. What is the kernel of phi? What is the kernel of phi? So what is the definition of kernel? So ker phi. Can you tell me what is the definition of kernel?
Solution of all x such that phi x equal to identity.
Phi x, right? Phi x equals to identity. So let me pick any member from the kernel. So let, just a minute. So kernel will consist of matrices, right? So a matrix A, B, C, D will belong to the kernel if and only if, when the Mobius in its image is this, the image is equal to the identity element of the group M, and the identity element of the group M is I, Z is Z. So is this line clear? You can write C or C infinity basically, because you can extend the definition of Mobius. Or right. Is this definition clear?
Yes, sir.
So if and only if you AZ plus B is equal to CZ square plus DZ, because, okay, let me not include C infinity, because this holds for every element of C. So I can compare the coefficients. So this will be valid when B is 0, A equals to B, and C is equals to 0, right? Because this is an identity. This is a, like, my point is that CZ square plus A minus DZ plus B is 0 for all Z in C. That means this is identity. This is an identity. So this will be 0 when C is 0, A minus D is 0, and B is 0. And that will imply C is 0, B is 0, and this. So what will kernel consist of? So therefore, core phi will consist of all those matrices of the form.
Diagonal matrix.
Right. Not diagonal, by the way. Scalar matrices. Right. So that A is in C. And this is nothing but, if I take A common, this is of the form 1, 0, 0, 1. A is in C. So this is actually, the kernel will be generated by the identity matrix, right? So okay, let me not write this way, and I have to write one more condition. This in C star, A cannot be 0. If A is 0, then this will no more be a member of this. Okay, so So this, or I can write this as, this is of the form A times the identity matrix of order 2 such that A is non-zero complex numbers except this. Right. So what is the point of doing this? You can also identify the Mobius transformation. So this, so I can say, so what I note is, by the first isomorphism or first homomorphism theorem, what I have, you can also identify, so this question by, if I call this kernel as a, this is a normal subgroup, you know that kernel is always a normal subgroup, so this is isomorphic to M. So you can also identify, so from the algebraic point of view, you can also identify the group of all Mobius transformation by the general linear group questioned by the normal subgroup, this one. Okay. So there is also a second part to this question which you can try. It's easy, or else I can explain you a bit. We have some more time left, I guess. So, or maybe I'll, okay, let me do it. So what is the second part also? There's some second part also to this question. Let SL2C be the subgroup of GL2C consisting of, so what is SL2C? Having determinant 1, consisting of all matrices of determinant 1 to show that the image of SL2C under phi is all of M. The second question is, what part of the kernel phi is in SL2? So to show phi of SL2C is indeed M. So what is the first part of the question? What is the first part of the question? So what is the first part? You are defining phi from GL2C to M. What is the second part? That instead of taking G, even if you are taking S here, then also it's fine. Nothing will change. This map will still be onto, and this will still be a homomorphism. And the fact is that, so if you remove GL2C by SL2C, the map will still be onto. So this is why the second part, this is what the second part says. If you remove GL2C by SL2C, this map will still be onto map. So how can you guarantee that? So can you tell me how to do it? See, the idea is very simple. Let A is equals to A, B, C, D in GL2C. I am taking GL2C. Okay. Then if you define another matrix with the help of A by taking, suppose this is a symbol I'm using, or I should not use this symbol. Okay, I'm using the matrix B. Just a minute. Okay, let me use this symbol A cap as 1 by determinant will this be a member of SL2C? Yes or no?
Yes, sir.
Yes, sir.
So your task is to show that. So to show phi of this is same as phi of A. If you can show this, are we done?
Yes, sir.
Right, because you already know that this is onto, so I'm just using this fact because this map is onto. So if you can, so given any A in GL2C, if you are defining A cap like this, then you are getting a member of SL2C, and then this map will be onto. Okay, so that the image of SL2 under phi is all of M. So that part is done. If you can do this. For the second part, what part of the kernel phi is in SL2C? So part of core phi. What is the question? In SL2. In SL2C is nothing but core phi intersection SL2C. So you have to pick all those matrices in core phi whose determinant is 1. So can you tell me what is the answer then?
Sir, mod A equal to 1.
Right, right. So this is nothing but all those, or AI such that mod A equals to 1. That's correct. So this part, so if you can say, so I can also say that M is isomorphic to SL2C questioned by this one. Suppose I am calling this as N prime. So this is N. So from algebraic point of view, this group of Mobius transformation can also be represented by this or by this. Okay, so keep this in mind. So why is this important at times? So if you want to study the algebraic property of M, you can study the algebraic property of G2LC questioned by a normal sample. So this is all about it. So that's all for today. Maybe in the next tutorial, if sir uploads some problem sheet, I'll discuss that to you all. Okay.
Hello, sir.
Yes.
So suppose take A equal to I, then mod I equal to 1. But sir, is it belong to SL2C? Because AD minus BC is -1 ना.
I did not get your point. Yes.
सर ये आपने लिखा है कर्नल फाई, मतलब AI2 जो है वो हमेशा SL2C में बिलोंग करेगा कि नहीं, बस ये मेरा क्वेश्चन है. सपोज A equal to I.
Okay, A equals to I. Okay.
Then I2 belong to SL2.
Okay. So AI2 is what? 1, 0, 0. Oh, this is I0, 0, I. So what is the determinant of this matrix?
-1.
Is I square. Okay, okay, okay. So I have to just, determinant should be 1, right? The determinant is -1. Okay, so you have, yeah, that's correct. So I have to just change this. This will only consist of 2
So
points.
actually, sir, it consists of number of solutions A square equal to 1, A square equal to 1 in C star.
Right, and that is nothing but plus I and minus I, right?
Yes, sir.
So this is nothing but, this will only have 2 matrices, 1, 0, 0, 1, and -1, 0, 0, -1, right?
Yes, sir.
No, yeah, you cannot take mod A equals to 1, that is right. right. It will only have, so it will only have plus I and minus of I2. Okay. Sure, it is correct. Okay, that's all for today. Meet in the next class then.
Hello, sir.
Yes.
Sir, what proof of L'Hopital rule in complex analysis?
Just a minute.
How